our final version of the fundamental theorem of calculus will be the divergence theorem. And the divergence theorem applies when trying to calculate the flux through a closed surface. So Stokes' theorem was applied to an open surface with a curve that was the boundary. The divergence theorem is going to apply to closed surfaces. So we're going to suppose that S is a closed piecewise smooth surface that bounds the space region T, and we're going to let the outer unit normal vector field N be continuous on each smooth piece of S. Then if the vector field F is continuously differentiable on that space region T, okay, the flux integral, okay, the integral over S of f dot n ds, is going to equal the triple integral over the enclosed space of the divergence del dot f dv. We're going to give you a sense of the proof of this theorem in a similar way to how we proved Green's theorem. So we're going to consider this theorem on a simple region, like a type 1 or a type 2 region in 2 dimensions, but we don't have those descriptors in this case. And so we're going to prove this for a simple case, and then you can see that you can follow the same steps in order to prove it for all the rest of the cases. So here, I'm going to let my vector field F be P, Q, R. Okay, then what is the divergence? Divergence in this case is going to be the derivative of P with respect to X plus the derivative of Q with respect to Y and plus the derivative of R with respect to Z. Well, we're going also going to look at what is F dot N. Well, F dot N in this case is going to be P times the first component of N plus Q times the second component of N plus R times the third component of N. So what we're going to prove in this case is that the surface integral of just the first component of f dot n, so P times n1 ds, well, that in fact is equal to the triple integral of, and then we would have the divergence, and I'm just going to consider the first part of the divergence. So dp dx. And then we're going to prove, or we would need to prove, that the surface integral of q times the second component of n ds is equal to the triple integral over t of dq dy dv. And then finally, we would want to look at the surface integral of r times n3 and show that that is equal to the triple integral over our region T of dr dz dv. If we can prove those three things, then in fact we can prove the divergence theorem. Well, I'm specifically going to look at just this part. We're going to prove the third part. And you can see that once we've proven the third part, then the proofs of the first and the second parts will be very, very similar. And the way that we're going to prove this is that we're going to look at a surface that has a specific shape. Okay? So what we're going to do is I'm going to draw a curve like this. Okay? And then another curve down here. And then a curve at the bottom. So I'm going to make a three-dimensional closed surface. Okay? And here, there's going to be a top, a bottom, and then kind of the lateral side. But in this case, I'm going to call the lateral side S2 and then the bottom S3. Okay, so I'm going to say that this top part of the surface is parameterized as G1 of xy. Okay, so I'm thinking about it as Z equals G1 of xy. Okay, and then the bottom, okay, that's going to be G2 of xy. Actually, so I'm going to reverse how I did this. So I'm going to call this one S3, the lateral one, and that one S2 to make it correspond. Okay. Well, the top of this is going to have a unit vector. So there's going to be a unit vector. Okay. We're going to call that NS1. Okay. The bottom is going to have a unit vector. We're going to call that NS2. And then the third surface is going to, that lateral surface will have a unit vector that kind of points horizontally. We're going to call that NS3. So our three-dimensional region is going to have this specific shape. Okay, so we're going to say that T be a region with boundaries. Okay, so we're going to have Z1 equals G1 of xy, and then Z2 equals G2 of xy. Okay, so that's the kind of bound surface that we're going to, or that's the kind of three-dimensional domain that we're going to be working within, bounded by, okay, Z1 and Z2. Well, let's see what happens when I try to do the triple integral over that region T of R sub Z dV. Well, I can describe the innermost integral as being from G1 of xy to G2 of xy. Okay, so this is, I'm going to write this as dr dz. So we're going to integrate dr dz, and then dz, and then dA, where that represents dx dy. Okay, so we're going to integrate over the region A, And then specifically, I'm going to pull out the z integral. The z integral is going to be from g1 to g2, as you can see from the way I've drawn this region. And if I do that, well, I'm going to get the double integral over a of r of x, y, and then z is going to be g1 of xy, or g2 of xy. Sorry, it's g1 of xy. This is actually going to go from g2 to g1. So g1 of xy minus r of x, y, g2 of xy. So what I've done is I've applied the fundamental theorem of calculus to just that first dz integral. Okay, the integral of dr dz is just going to be r, and I've evaluated r at g1 and g2. Okay, so that is the triple integral for the divergence. Well, what about the other integrals? What about the surface integrals? So we have to integrate over 3 surfaces. So the integral, okay, over the first surface, S1, of r times the third component of n3, is going to just be the double integral over a of r of, now I'm going to evaluate on the surface. So if I'm on the surface S1, that's going to be r of x, y, g1 of xy. And then the third component of n is just going to be 1 because that unit vector is pointing up, dA. So this is since n3 is equal to 1. Okay, for S1. Well, let's keep going. If I do a double integral over the surface of S2, r n3, then I'm going to get a double integral over a of r. I'm going to evaluate that at x, y, and then g2 of xy, because that's the surface that I'm on. That gets multiplied by the third component, okay, of n, which points downward, so that's going to be -1. And then that's going to be integrated dA, and that's since n3 in this case is -1 for S2. And then finally, if I integrate over the lateral surface n3, it's going to be rn3, okay? Well, in this case, that is going to be 0, okay? Because I'm going to have a horizontal vector here for n3. Okay, specifically, it's got to be horizontal. Okay, so in this case, rn3 is going to be 0. And so the integral is going to be 0 since n3 is equal to 0 for S3. Okay. Well, now, if you look at that, what I've shown is that this piece of that double integral matches this piece. And then in a similar way, this piece matches this piece. And so I have actually shown that for this specific kind of region, that the triple integral over t of dr dz dv is in fact going to be the surface integral of r times n3. So I have now shown that the divergence theorem works for this kind of region. Okay, so then we're going to repeat for other kinds of simple regions. And that, in fact, will prove the divergence theorem.